Hey guys, in this video we are going to be talking about implicit differentiation. Alright, so to talk about implicit, we need to know what an implicit function is. Alright, and so it's counter to an explicit function. This is much easier to describe. So an explicit function is something where we have a direct rule where for any input x we get out exactly one output y, and we can write it as an explicit formula. So, y equals 2x plus 3, y equals x squared plus root x, y equals e to the x plus sine x times tangent x. All of these, the second you know x, you just plug it in on the right side and you get out your y. Okay, so this is an explicit function. On the other hand, this is not always the case. So you could see something like 4y plus 2x is the natural log of x. So in this case, right, the second I plug in x, it's not clear what y is. I have to get y by itself, right? Well, that would be turning it into an explicit function. So here, y implicitly depends on x. And then in this case, we can actually solve. So we could do 4y is ln of x minus 2x, and so y is ln x minus 2x over 4, and then this becomes explicit at this step. But this will not always be the case. We can have implicit functions that cannot be turned into something explicit. For example, a circle. So if you have a circle, this is one we'll talk about here soon, you're not going to be able to get y as a function of x. Yes, you can get y by itself, but we know that a circle is not a function because of that old vertical line test, right? Another example would be like xy plus sine of y squared equals 2y plus x. So here, there's no way, you can get the y terms on one side, but because this y squared here is inside sine, there's no way you're going to be able to divide out and get y by itself and solve for it in terms of x. So these guys are implicit and will remain implicit. All right, so let's go ahead and talk about implicit differentiation. So again, we said the circle is implicitly defined, which is because, yes, you could write y in terms of x, but what would we do? We would need the plus or minus the square root of 4 minus x squared, and that's not a function, right? One gives us the top half, one gives us the bottom. So we think of this as an implicitly defined function, but it still makes sense to talk about the slope, right? We can ask what is dy dx, because as x changes, y will change. And of course, we have tangent lines all over the place here, right? And so we can talk about slope here. So the question is how to calculate it. So taking the derivative with respect to x of x squared and 4 is easy. We know how to do those. The real question is, what is the derivative with respect to x of y squared? So here, the trick is to think of y as a function of x, right? So as x changes, y is going to change. So there's this dependence of y on x. We don't have a formula, but we can write y equals f of x, just meaning it changes depending on x, okay? And so if we rewrite this using that, we get d dx, derivative with respect to x, of f of x squared. Well, this should remind you of the chain rule, okay? So f of x is our inside function. Our outside function is, we're squaring here. And so what do we do to take the derivative with the chain rule? Well, it's derivative of the outside, so the squaring, well, u squared goes to 2u. And so this is 2u is f of x, your inside, times derivative of the inside. My inside is f of x, so its derivative is f prime of x. And then remember that f of x is just y, so this is exactly 2y dy dx. So you're going to notice this dy dx guy pops up every time you do implicit differentiation, because you're always doing this mini chain rule on y. So anytime you have a y in part of the equation, when you take the derivative, you'll get a dy dx popping out. Okay, so let's go ahead and finish out this example. So if you want to find dy dx, well, we're just going to go ahead and take the derivative with respect to x of everything here, okay? So x squared becomes 2x. We just showed before that this is 2y dy dx. So it's basically, you know, what you would hope for in terms of y squared goes to 2y, but because y is some other function, the chain rule tells us we spit out this dy dx as the derivative of the inside. And this is equal to 0, the derivative of 4. And then we want to solve for dy dx. So dy dx is negative 2x, and then we would divide by 2y. We can simplify, and we get negative x over y. Now this is going to be common. Note that this is going to still have y. That is okay. Because it's implicit, we can't really expect it to only become an explicit function after taking the derivative. It's okay to still have this. Okay? So this is our end answer. And let's check that this kind of matches stuff on the graph. So if x equals 0, aka if you're on the y-axis, then dy dx is 0. Well, what do we see? We're on the y-axis here. We have horizontal tangent lines at both points on the y-axis. If y is 0 and we're on the x-axis, what do we notice? Well, then we're trying to divide by 0. So this doesn't exist. Well, it makes perfect sense over here, right? We have vertical tangent lines when y equals 0. And you can see kind of when x and y are the same up to a sign, you know, midway through each of these quadrants, you're going to get either 1 or negative 1 as your slopes here in yellow, okay? So it checks out. All right, so for the first warm-up question, I just want you to look at these four equations here and decide which of the following define an implicit function, y as an implicit function of x. There may be more than one. Infinity will have this as a multiple choice question, okay? All right, so for the second warm-up question, I want you to find dy dx, the whole formula, not just at one point, for the hyperbola y squared minus x squared equals 1. All right, so those are the two warm-up questions. So now I'm just going to do one more example if you want to keep watching where it's a little bit more complicated, okay? All right, so now let's do a little more challenging example. So we want to find dy dx for the function xy equals e to the 4x plus e to the 5y. So let's just work left to right. So we're going to take the derivative with respect to x of everything. All right, so start by doing that. Now if we have xy here, we need to use the product rule, right? We have a product of things. So we'll have x times, so original x, times derivative of y, which is just dy dx, plus derivative of x, which is 1 times y, equals, so derivative of e to the 4x, well, this is a chain rule, right? We have 4x as our inside function, so when we take the derivative of e to the whatever, we get e to that, so we're going to have e to the 4x, and then times 4 because that's the derivative of 4x. And then for the same reason, we'll have 5e to the 5y over here, but we have to do one more thing, right? When we have the derivative of 5y, we get the 5, but then the derivative of y is dy dx. So remember, like anytime you're seeing that y, we're popping out a dy dx because of that chain rule for the implicit. Okay. So we want to solve for dy dx. So we have two terms which have dy dx in them. We should try to get those together so that we can then factor out a dy dx, right? If our end goal is to get dy dx by itself, that seems like our only option. So I'll just go ahead. Okay, so we've got dy dx. We have it times x over here. And if we subtract that guy over, we're going to get minus 5e to the 5y equals, So the 4e to the 4x stays on the right side, and to get the non-dy dx stuff over here, we will subtract that y away. And now, well, this is a product over here, so we can just divide, right, and get dy dx by itself. So we have 4e to the 4x minus y divided by x minus 5e to the 5y. All right? So there we had to use chain rule, some product rule. So this is a little more complicated example and hopefully gives you a better idea of how to do these in general. All right, thanks for watching.